Okay, Marco, we are ready, right, with the online audience? You can hear me online. You can, more or less. Should we still check this, or?
I'll try. I think the volume is low.
Okay. I mean, I can also talk a little louder. Do you want to check still? Can you hear us okay in Zoom?
I think it's okay.
It's okay. All right, let's get started. Perfect. Well, then it's my great pleasure to welcome you all to. Does this work? It works, right?
Yeah.
To welcome you all to today's colloquium by the Aleatoric AI Center. So welcome everyone here in the lecture hall and welcome everyone in the online audience. Just briefly, so a few logistics. So we have the talk now, and afterwards we invite all of you to stay around for some snacks and drinks, which we just serve outside. And we are recording this seminar, this colloquium, however not the Q&A, and we'll be taking some photos around here. So that much about the logistics. Now it's my great pleasure to welcome Eyke Hüllermeier here on behalf of our AI Center, or the Board of Directors of the AI Center, who is our today's guest and giving our AI colloquium. So Eyke is from Munich. He's a professor at LMU in Munich, where he has the chair for artificial intelligence and machine learning. And originally, I learned Eyke is from North Rhine-Westphalia, actually, from Ostwestfalen. And he also received his PhD from that region, actually from the University of Paderborn. And I also learned today that you actually had professor positions at multiple universities, and I need to look this up. So you had professor positions in Dortmund, in Magdeburg, in Marburg, in Paderborn, and now you are in Munich. So you've seen many universities, and we are particularly happy that you are visiting us here today and tomorrow in Aachen. So a few words about Eyke. So in addition to the professor positions, he was also at a Marie Curie Fellowship and staying some time in France and in Toulouse. His interests are in, I guess, the foundations of artificial intelligence, and today we will hear about machine learning, but I also learned from you that you have, when you started not working on machine learning, so you have a quite a broad perspective on artificial intelligence, and we are looking forward to hearing today about your current research. Eyke has a number of positions and honors. So he's the editor-in-chief of Data Mining and Knowledge Discovery Journal. He's also the president of the European Association for Data Science. And he's also on the strategy board of the Munich Center for Machine Learning, which is between LMU and Munich, I believe. As well as several other positions that I'm not going to read out now because I don't want to take away more of your time. So Eyke, we are very happy to have you here and looking forward to your presentation.
Thanks also for inviting me here. It's always a pleasure to come to Aachen. I remember my very first scientific conference was in Aachen. So that was back in 1994. Most of you are young people here. that was almost still the time of good old-fashioned AI. And this is maybe a good keyword to start. Today I'm going to speak about uncertainty in AI, and more specifically uncertainty in machine learning. And this topic of uncertainty has always been an important topic in AI, almost from the very beginning. Already the good old-fashioned expert systems noticed quickly that it's important to deal with uncertainty because the world around us simply is full of different sorts of uncertainties. There is also an old established conference in the field called Uncertainty in AI, which is now already over 40 years old. But the topic has received again increasing interest in the last couple of years because, of course, nowadays we see more and more AI applications and in particular machine learning applications really in the real world, and many of them are safety critical. So here you see a simple example, a medical application. This is a typical machine learning scenario. We have a set of training data, in this example, a set of X-ray images labeled positive, negative, depending, for instance, whether a certain disease is present or not. The X-eyes are the images, the Y-eyes are the labels, and from this training data, via a process of model induction, we are learning a predictive model. Could be a neural network, but could in principle also be any other sort of model, and hope that this model will generalize well beyond the training data it has seen, so that for every new query instance, a new X-ray image, for example, it will give us a correct prediction. Modern predictive models do not only predict a category, do not only give a deterministic answer, they typically provide us a probability. So here, for instance, the network could tell us this is a positive case with probability 0.9. And that's good information because it tells us something about how certain or uncertain our model actually is. An important question in this regard, of course, is how much can we trust this 0.9, which by itself is only a prediction. That's why we have a hat here, a p-hat, of a ground truth conditional probability, positive label given the query instance. And it turns out that quite often we can't really fully trust and rely these uncertainty quantifications. Here is a simple example. We trained a state-of-the-art neural network and showed it these images here from a fashion data set. And here it's a predicted umbrella, here it predicted skirt, which is of course completely wrong, as you can easily see. These examples are handpicked, so in general the performance is quite good, but these are exceptional cases where the system makes a mistake, a big mistake. Now you could say mistakes can happen. We also as humans, we do mistakes sometimes, not in these examples, but in other cases. But what is really the problem here is not that the system makes the wrong prediction. The problem is that at the same time, the system is suggesting a very high confidence, close to 100%. So it's very convinced of its wrong answer, and that's not good. This is not something we would call uncertainty awareness. We as humans, we typically notice when we are in a situation where we are not really certain, yeah, and then we better, I don't know, say nothing, most of us at least, yeah, or at least express a notion of uncertainty. We have similar problems in many other types of AI systems, like, for example, large language models which hallucinate from time to time, yeah. And this problem, or this, let's say, this quest for being able to also say don't know, we also have in many other applications. So for instance, imagine you have a self-driving car, which is learning to recognize traffic signs, then of course you also want that if the car is driving in a new country with a new sign it has never seen before, Australia, for example, with a kangaroo, or like this arrow here, this curvy arrow on this sign, then it would be better, much preferable, if the system says, I don't know, instead of engaging in some sort of wild guessing or so and saying it might be this sign because it somehow looks similar with an arrow on or whatever. Yeah. By the way, can you hear me well? I have the feeling that somehow the audio, okay, I have a small echo here, but then it's fine. So this uncertainty awareness has something to do with the distinction between different types of uncertainty that are commonly distinguished in the realm of uncertainty in research on uncertainty representation, quantification, and in particular with the distinction between what is called, and this is my main topic today, aleatoric and epistemic uncertainty. Here is a simple example illustrating this distinction. By aleatoric uncertainty, we mean inherent randomness, stochasticity. Yeah? Like this is a prototypical example, you flip a coin and you can't predict whether it's going to land head or tails. On the other side, if I ask you, for instance, what is the meaning of the word kichwa in Swahili? It's either head or tail, I can tell you, but which one is it? Most of you have no clue. And if I want a probability from you, you will maybe also give me 1/2 or so, right? But the important difference now is that this uncertainty about the meaning of this word, you can easily get rid of. Just look into the dictionary or ask Google or whatever, you can get rid of. And this is what we call epistemic uncertainty. This is uncertainty due to a lack of knowledge. A lack of knowledge that we can get rid of. And the importance, by the way, to distinguish between the two was already highlighted by the great Quantification, by a famous statistician who said, not knowing the chance of mutually exclusive events and knowing the chance to be equal are two quite different states of knowledge. So here we know, we do have full knowledge about the stochasticity. We know the probability is 1/2, 1/2, when the coin is fair, but here we know nothing, basically. So here is again a short summary. Aleatoric uncertainty is uncertainty due to inherent randomness. It is a property of the data generating process, of nature, so to say. And as such, it is irreducible. We can't do anything about it. By epistemic uncertainty, we mean uncertainty due to a lack of knowledge. This is a property not of nature, but of our AI agent, of the epistemic state of the agent. And the principle, it can be reduced on the basis of additional information. Now, this distinction between these two types of uncertainty is arguably also important in machine learning. So here, for instance, imagine we have seen some positive cases, some negative cases, and we have to make a prediction for the new yellow one here, which might be an X-ray image or an embedding of an X-ray image. And then we say, okay, difficult to say, seen little data only so far, no data really close, hard to say, hard to predict. Yeah. Here on the right-hand side, the same point, but now after you have seen lots of data, and again, you will be very uncertain whether it's a positive or a negative case, but now you know that you have a good reason to be uncertain, right? You have confirmed, so to say, that this is a, I don't know, 1/2 case because the two classes are highly overlapping in that region. One important side remark, because this is very often a bit overlooked also in the literature, it's not only the amount and the quality of the data that is important for the question how certain or uncertain you are. It's also, of course, the assumptions you make, the induction bias, so to say, you start with. So, for example, if you know or you have good reason to believe that the two classes can be separated by a simple linear model, then even this little data might be enough to convince you that this is a positive case. Basically, because all models that are more or less coherent with the data will predict positive. If you weaken your assumptions and you also allow for nonlinear models, for example, a quadratic or so discriminant function, then the case is again more uncertain because there are some models which are coherent with the data and which predict positive. This one here, for example, and others also coherent with the data which predict negative. Yeah. And this is also intuitively plausible. The more knowledge you start with in the beginning, the more the data is telling you, the stronger conclusions you can draw. Because obviously that's also a bit connected to listen a priori from Kant. So here's an overview. I will use these type of illustrations from time to time of learners of different levels of uncertainty awareness. This triangle here, for instance, this triangle, this is representing the probability simplex, the two simplex. It's just a projection of the two simplex. So every point in the triangle is a probability distribution on three outcomes: y1, y2, y3. So, for example, imagine you want to predict, I don't know, the outcome of a football match, win, loss, time. Three possible outcomes, and every point here encodes a probability distribution, assigning three probabilities to the three possible outcomes. A deterministic predictor is the least uncertainty aware. It just says we lost time. Yeah, deterministically, so it predicts the corner points here, the red corner points. A probabilistic predictor is more uncertainty aware. It can predict a probability distribution, so assign a degree of probability to every outcome. So it can predict points here in the interior. Yeah, for example, the red one, which will probably be a little bit away from the ground truth probability, which, by the way, we assume to exist. This is an assumption we make and which is debatable, but a common assumption in machine learning, there is a ground truth conditional probability of y given x. So this probabilistic predictor maps from our instance space to the set of probability distributions over the outcomes. Here on the right, we have what I will call a second order predictor, which is able to represent, in addition, uncertainty about its probabilistic prediction. For example, this is this capital Q here, for example, in the form of a second order probability. That means the probability distribution over the probability distribution. So every point here again is a probability distribution. So we can put a probability distribution over the probability distribution over the simplex, or in other ways. So for instance, there is a notion of creedal set in the uncertainty literature, which is just a set of probabilities. So there are various things. I am mostly going to speak today about second order probability distributions. And this one here on the right, this is, we would say, the most uncertainty aware predictor. Yeah. And if you have to, I don't know, predict the outcome of a football match and you're not a football fan, or you don't know the teams very well, yeah, you would prefer maybe to use the right one in order to express your ignorance or your partial ignorance. How would you represent total ignorance? You know nothing. how would you? I mean, here with a probabilistic predictor, you can't because you always have to commit to a point. Maybe you choose the middle point, which is the uniform distribution, but then you can't distinguish anymore between I am certain that this is a uniform distribution or I know nothing. That's the point. Here you are more expressive. So how would you?
When you color to try computing.
Yeah, exactly. The question is, do you work, for example, with trivial sets, or do you work with second-order probability distributions? When you work with second-order probabilities, you take probably the uniform distribution over the simplex. And you can again argue, but I'm not going into this discussion today. Yeah, it's a big debate since decades whether probabilities are actually good mathematical means to represent ignorance. But anyway, yes, this is what you would do. There was a question.
This second order predictor, is that equivalent to a Bayesian model or is there a difference?
I will come to this on the next slide, or maybe the one after the next. But yeah, the Bayesians among you will immediately be triggered maybe by this illustration. Here is the same representation, but a little bit simpler for the binary case. This is easier for drawing. So here our probability simplex is just the unit, yeah, and we predict 0, 1 loss win, and the point here, the p is the ground truth probability of the positive class. And a second order predictor would be a distribution over this one simplex. And yes, the important thing I mentioned already, this is our assumption. We can't get rid of the first order uncertainty, which I'm going to call the aleatoric uncertainty, because, for example, we cannot deterministically predict the outcome of a football match. We can't do that deterministically. There is always a probability, our ground truth probability. But we can reduce our epistemic uncertainty. So, for instance, you can inform yourself. So, for example, the last World Championships at my chair, we did a competition, so everyone was tipping the outcomes of the football matches, and then we determined the winner. There was a somehow complicated system. I was doing well in the beginning, but imagine who won in the end. I can't know. My secretary won, although she knows nothing about football. I don't know how she did it, but she was doing, she was researching on the web and so on. So she was informing herself. Yeah. So she reduced her uncertainty, and in the end, she was doing really well. Okay. So now my main topic today will be about representing this second order uncertainty, epistemic uncertainty. But before I come to this, let me say a very few words about representing first order, namely aleatoric uncertainty. Just one or two slides. So first order uncertainty, again, we have a probabilistic predictor. So for instance, you train a neural network to predict X-ray images, and of course, what we would like to have is what we call well-calibrated probability. So if our network says 0.7, then we want that this 0.7 is really, this h of x, this prediction, is really close to the true conditional probability of y given x. And we can, let's say, make the learner or incentivize the learner to predict these ground truth probabilities, at least theoretically, if we train it in the right way, especially by using a good class of loss functions, which are called proper scoring rules. Theoretically, you can prove that the proper scoring rule, like for example, cross entropy is an example of such a proper scoring rule, the Breyer score, there are various examples of proper scoring rules. You can prove that if you penalize your learner for incorrect predictions with the proper scoring rule, you incentivize it to exactly predict the contribution probabilities. I'm mentioning this here also because I will later come back to these proper scoring rules. Who heard that name before? A few, okay. Now, this is theory. In practice, this doesn't always work. What you often observe in practice is that your learner somehow produces bias, estimates bias predictions. When you plot, for example, the predicted probability versus the true probabilities, you often, if you know the true probability, which you normally don't, but if you know, then you often see things like this here, where the learner is overconfident, so it predicts more to the extremes, 0 or 1, or you have a learner that systematically overestimates probabilities and such things. And this is why one branch of machine learning research currently deals a lot with what we call calibration. Calibration methods basically try to rectify these biases by, for example, learning in a post hoc manner so-called calibration function, which takes a predicted probability as input and produces a hopefully better adjusted probability as an output. This is a good survey on this topic. Okay, I'm not going to say more about first order probability prediction. I just wanted to make this point that even this is already not a very easy thing to do, and still also a topic of active research, especially when you want to calibrate multi-class classifiers. These examples are all binary. My examples are mostly binary, but if you have multiple outputs, yeah, win-loss tie and even more classes, then you can imagine it gets even harder. Okay, but now let me come to the main part of today, the question of how to represent epistemic uncertainty. So here our question is, how can we train machine learning models which are able to represent their epistemic uncertainty in a faithful manner, which are uncertainty aware in that sense. So we do not want, this is clear, we do not just want to have, we are basically interested in quantifying predictive uncertainty. There are various other sorts of uncertainty in a machine learning context that you may think of, but we are now mostly interested in quantifying the uncertainty of the predictions that our learner makes. We don't just want to have a deterministic prediction, that's for sure, but we also don't want just to have a first order probability, a precise probability. What we want is such a capital Q, which is a richer second order representation, and the learner that is producing such a prediction, I'm going to denote by this capital H here, capital because it's second order. Now, this is the topic of active research, and various approaches have been proposed for that purpose in the literature. And I'm going to speak today mostly about this second approach here, which I call generalized loss minimization, and I'm telling you more about this in a minute. But first, of course, you can't avoid the Bayesian view, because for a Bayesian, the problem is basically solved anyway, more or less. Yes, you can go Bayesian. Yeah, Bayesians basically have already this second order representation. You remember the Bayesian approach to machine learning or statistics in general. In the Bayesian approach, you do not commit to a single predictive model. What you do is you maintain a distribution over your hypothesis space, assign probability to every predictor. Then, if you have a query X for which you want to make a prediction, then you obtain what is called the posterior predictive distribution, which is just the image of that distribution here under your mapping H. And this is basically what we want. Yeah, this is the second order distribution. When you observe data, you will turn your prior distribution into a posterior distribution, which will be more concentrated. And if you want to have a point prediction, you do Bayesian model averaging. Yeah? So basically, it's all there. Provided you are happy with a purely probabilistic approach, you could say that's basically fine. And yes, the Bayesian approach is definitely a good, a theoretically very appealing approach. Computationally, maybe a bit problematic. Yeah? This is why people in the recent time have tried to develop various Bayesian, or at least I would say Bayesian-inspired methods, which are computationally more tractable. And in particular, in combination with deep learning and neural networks. So a standard neural network makes point predictions. Every weight here is a point, and it will also produce a point probability as a prediction. Bayesian neural networks is one way to go, let's say, Bayesian. In Bayesian neural networks, the weights at the edges of the neural network are replaced by probability distributions. And for example, Gaussians, yeah, and they have two parameters, and the collection of all these parameters for all the distributions, for all the weights, they determine your hypothesis space. That's a parametric space. And such a Bayesian neural network will produce you distribution, which is the second order distribution, in this case a distribution over the precise probabilities as an output. Methods like drop out, drop connect can also be interpreted in this Bayesian spirit, yeah, where you randomly kick out edges or nodes. Then if you kick out an edge, for example, it's present with a certain probability and absent with a probability, and then the weight is 0. Can also be interpreted in that way and will also deliver you something second order. These methods have been used quite a lot in the recent past. They remain computationally intense, so you can't do exact inference. You still need to do approximate inference using sampling techniques, for instance, MCMC, Laplace approximation, variational inference, or whatever. Yeah, there's a lot around and a lot of also still research going on in that field to make that work and computationally tractable. You can do it even easier by training an ensemble of standard neural networks. If you collect all the distributions, you also get a kind of second order representation. You can see basically how much the different predictions agree or disagree, and this tells you something about, this is the intuition about the epistemic uncertainty. Still, if you train neural networks, might be computationally costly. Also, there is no really good theory behind. You can also interpret it in a Bayesian way, hoping that the ensemble will somehow represent your posterior distribution well, but okay, it's more hope than theoretical proof at that point. Yeah. Still, these methods are quite fashionable these days. Now, I would like to speak about in a bit more detail about approach that has become quite popular recently and on which we obtained some, I would say, interesting results, which I would like to explain you today. These methods, I would call them second order risk minimization, or basically second order risk minimization. They have been introduced in the literature under the name of evidential deep learning, which is a kind of misnomer, I would say, and also meanwhile there are people complaining about it, because this notion of evidential machine learning, or more generally evidential something, is in the literature very much connected to the mathematical theory of evidence, which has been basically developed by Dempster and Schaefer. Maybe some of you heard about the Dempster-Schaefer theory, or the theory of evidence or belief functions or whatever. This has basically nothing to do with it. Still, it's called evidential, and not everyone likes this. But anyway, so the idea now is the following. We just talked about the Bayesian approach, and the Bayesian approach is costly because it always has to go via this distribution on the entire model space, hypothesis space. Now, the question is, can't we predict more directly such a second order distribution on the second order? So can't we, for example, train a neural network which takes an X-ray image or whatever as an input, and then predicts us a second order distribution, like here? Of course, this distribution must be somehow parameterized. Yeah, we could, for instance, take a Dirichlet distribution here. A Dirichlet distribution for the binary case has two parameters, alpha 1, alpha 2. Both equal 1 give you the uniform. The higher you make the values, the more peak the distribution will become, and the more different the values, the more skewed. So at least we could represent such a predictive model. We could represent it. The question is, can we make this neural network predict meaningful alpha values and therefore meaningful second order distributions on this epistemic level? Okay, so let us formalize the problem a little bit more precisely, more formally. The idea is, the question basically is, can't we do what is the most straightforward and the most common machine learning approach, namely training a predictive model by empirical risk minimization or variance of empirical risk minimization? So given a standard training data set, some xi, yi's, images with labels, for example, can we train a second order predictor which maps instances to second order predictions, probability distributions over probability distributions? By doing empirical risk minimization or regularized risk minimization, if you want, that means that we find a model by minimizing what we call in machine learning the empirical risk. And the empirical risk is just the loss on the training data. But now, of course, when we have a second order predictor, capital H, and we observe outcomes yi, we need a loss function that compares the second order predictions with the outcomes observed. I call this loss function here LE. The E stands for epistemic. So we need an epistemic loss function. Yeah, can we find such a model by minimizing empirical risk for a suitably chosen second order or epistemic loss function in such a way that the predictions, in a sense, are meaningful? So our learner really represents its epistemic uncertainty in a faithful way. So, of course, now the question is, what do I mean by faithful? We came up with a couple of criteria, which are not so important now. Here, I just, as an illustration, at least what you would expect of a faithful epistemic learner is that in the beginning, when it has seen little data or no data at all, it will represent the highest epistemic uncertainty, for example, by taking the uniform or the probability simplex. Then, when it sees more and more data, epistemic uncertainty will reduce. That means the second order distribution will get more condensed around the ground truth probability, and in the limit, when the sample size goes to infinity, we would expect that the second order distribution will peak around the ground truth probabilities and converge to a delta Dirac. Put all the probability mass on the ground truth first order distribution, ideally. So this approach, this idea of doing second order risk minimization, it is well motivated because at least it also works for the first order. And I mentioned these proper scoring rules already in the beginning of my presentation. We know, or we can prove that if we train a probabilistic first order predictor by doing empirical risk minimization with a loss function LA, A stands here for aleatoric, which is a proper scoring rule, then we incentivize the learner to predict ground truth probabilities. Yeah. So, and this is because we can show that if you take the expectation of this aleatoric loss function, the expected aleatoric loss when our learner predicts P, and you take the expectation over randomly sampled outcomes Y, and the learner knows that the samples are, the learner knows or believes that the samples are taken according to P, then the best we can do is to predict the P and not any other P head. Yeah? When it predicts any other P head, the expected loss can only increase. This is the distinguishing property of proper scoring. So in theory, it can't do better than predicting the ground truth probability. Now, what we obtained in the last couple of years is a series of actually negative results showing that this idea, this whole idea of second order loss minimization is really theoretically flawed, and in a sense it cannot work, at least not in theory. This is maybe a bit disappointing on one side. On the other side, I like these negative mathematical results actually because they often give you insight in what's going on, and yeah. So we have shown formally that this approach is flawed for a specific type of second order loss, which is commonly used in the literature, where you define your epistemic loss in terms of the expected first order loss. So you take the first order loss LA and you lift it, so to say, to the second level by defining your second order loss function as an expectation of the first order loss where the P is sampled according to your second order distribution Q. But also, this was our first result. But then we generalized it and we even showed it for any empirical loss. So what we showed, a bit simplified, I'm not going to show you the theoretical results in all the details, but what we basically showed is that such an epistemic loss that incentivizes the learner to make meaningful predictions, second order predictions, cannot exist. So this is a non-existent result. And once again, now you may wonder, what do you mean by meaningful? Yeah, and in order to, I will get a bit more concrete on the next slide. What we concretely mean by this. Let me first just to complete this story about this elementary learning, say that, so theoretically, at least this is our opinion according to the results we currently have, this approach cannot work. Still in the papers, there are still published quite a number of papers on this topic. You see good results, experimental results. To some extent, I think there are good empirical results because I don't know whether I should call it cheating, maybe that's too much, but theoretically we can show that in most cases our second order learner degenerates to first order learner by pretending to be totally certain about the true conditional probability. What people do in the literature is they regularize by penalizing a prediction for deviating from a uniform distribution Q0. So if they give a second order prediction Q that deviates from the second order prediction, that's penalized. And the more you penalize it, of course, the more you incentivize your learner to pretend to be uncertain. And then when you play with alumni in a clever way, you can achieve what you want. So this is a little bit doubtful. On the other side, this nicely shows, in a sense, that what we of course would like to have ideally is a learner that represents its epistemic uncertainty in a really objective way. But the question is whether this can really work, because, as I said in the beginning, our understanding is that epistemic uncertainty is a lack of knowledge. So it's a property of the learner, not of the data generating process. So in one way or the other, I would say you can't avoid to externally somehow tune or manipulate your epistemic uncertainty. And it's also done in the Bayesian approach, when you start with a prior. In the Bayesian approach, I would only say it's done in a more explicit way, and you don't hide it somehow. Okay, so here, just to complete, here is our really the core theoretical result, where we lift this notion of a proper scoring rule to the second order. We introduce the notion of what we call a second order scoring rule. And a second order scoring rule is basically defined in the same way as the first order scoring rule, only now for second order distributions. So we have two expectations here instead of only one. We first sample a P from the capital Q and then a Y from the P. And we look at the expected loss of our epistemic loss function. And what this inequality here is telling us is basically the same as for a first order scoring rule. It's basically telling us that if our agent believes, let's say, holds a second order belief Q, or knows that Q is the right second order representation, and it knows that the first order distribution is summed from Q and then the outcome from P, and it's penalized according to this loss, then we would like that this learner, the expected loss is minimal for the Q and not any other second order representation. So we want again this inequality to hold. And our main theoretical result is telling us that such a loss LE cannot exist. This is basically this non-existence result. And one reason, again, I don't have the time to go into that much detail, but one reason here for this problem that this cannot work, directly predicting the second order distribution, is basically the lack of information we have on the first level, because we never observe first order data. We never observe an X with a ground truth probability. We only observe an X with an outcome sampled from the ground truth probability. And so there is a gap between the second level and the ground level, which causes ambiguities. So this is a very high level explanation. There are many other methods. So I don't want to, I just want to make sure that don't misunderstand this result. It doesn't mean that the whole field is somehow flawed. There are many other methods, and there is hope that they will work. It's only this particular approach that, in our opinion at least, doesn't really work very well. Okay, I am not going to go through this list in the interest of time. And just very quickly, do I still have 5 minutes or so? 5 minutes, just very quickly, a few words about uncertainty quantification. So I do make this distinction between uncertainty representation and quantification. Representation, we basically have been talking about now all the time. How do you represent, for instance, your epistemic uncertainty in terms of the second order distribution or whatever? What we mean by uncertainty quantification is to quantify your amount of uncertainty in terms of a number, a single number, which is often very useful to have. You all know Shannon entropy, yeah, which is the most common uncertainty measure for standard first order probability distribution. We would like to have the same for second order. So if we have given a second order prediction, capital Q, we would like to somehow be able to quantify in terms of a single number, or actually three numbers, the amount of total uncertainty that we associate with that representation. And we would like to distribute that number into an aleatoric and an epistemic part, ideally such that this decomposition is additive. The total is the sum of the aleatoric and the epistemic. Yeah. And ideally also these measures, this is common in the branch of the literature, are axiomatically justified. Like Shannon entropy, for example, follows from three simple axioms as a unique measure of uncertainty. Question?
So how could the program know that it is giving it the uncertainty that it is or it is not able to answer because there is a lack of knowledge? How will the program know? It's just the program just wouldn't know that.
Yeah, I mean, but this is more the question of representation, and we've just been talking about. And your doubts, I mean, are confirmed by our negative result. It doesn't really work. Yeah. Other methods, I mean, work to some extent. But now we ask basically a related, but perhaps even, I don't know, simpler question. I give you a Q. I say, this is my distribution, second order, and please assign numbers that quantify total aleatoric and epistemic way in such a way that we have this additive decomposition. So the most common approach to do that currently in the literature is making use of a result that is well known in information theory, namely that entropy decomposes additively into conditional entropy and mutual information. And the idea is to take conditional entropy as a measure of aleatoric uncertainty and mutual information as a measure of epistemic uncertainty. So if we call that we are given the Q, we sample first order distribution P from Q and then an outcome Y from the P, and then we could say our total uncertainty about the outcome is simply the entropy, the Shannon entropy of this distribution on Y. And this is the entropy of the average distribution, average first order distribution P bar. If we know the P, then we may still be uncertain about the outcome Y, but then the uncertainty is purely aleatoric because we know basically everything, we know the stochastic process, and the uncertainty is aleatoric, and therefore we could say that the conditional entropy of Y given P, which is the integral here of the entropy on P according to the measure Q. This is a meaningful measure of aleatoric uncertainty, and then if we want to have this additive decomposition, there is only one way to define the epistemic uncertainty, namely as a difference between the two. And this is known as the mutual information in the literature. Yeah. So this is a common approach. Again, we criticized it in a recent paper. I don't know, we are a bit critical apparently in the recent past. But it also can be criticized again for some reasons. I just wanted to highlight here once again that also this problem of uncertainty quantification is a tricky problem that is not so easy to solve. And I just want to give you an idea here with a simple example for why it might be not so easy to make a meaningful statement about your uncertainty and disentangle it into these two parts, aleatoric and epistemic. So, for example, if I give you this sequence of numbers here, you know, all these from school, this number completion games, yeah. If I say 2, 4, 6, what is the next number? You will say 8. I will ask you why, but okay, it's a good answer anyway. And now, if I give you this sequence of numbers here, and I ask you for the next one, what do you say? It's hard to say.
No idea.
No idea. Yeah, this is what I want. Yeah. We all agree that you are uncertain about the answer. That's at least what we agree on. But now my actual question is, your uncertainty about the answer, is it more of aleatoric nature or is it more of epistemic nature? Yeah, is it more or both? To some extent, both.
And it depends how you generate these numbers.
Yeah,
Good.
yeah, that's pretty accurate actually.
Yeah. Yeah, the Bayesian, it's a clever answer. Yeah, I mean, this is the point I wanted to make. So it could be that this sequence of numbers is purely random. It's a random sequence of numbers. In that case, you have no way to learn any pattern and no way to predict. And the uncertainty would be purely aleatoric. But it could also be that this is a deterministic sequence, pseudo-random numbers, not random numbers. In this case, and by the way, this is exactly what I did here. I computed this sequence of numbers deterministically. In this case, you do have a chance to learn. There is nothing stochastic here, and all uncertainty is epistemic. Yeah, if I give you a few more numbers, maybe you get it. This law here. Now the important point is that you can't know. You can't yet know. And what does that mean? This means that there is definitely epistemic uncertainty involved, but more importantly, as soon as you are epistemically uncertain, it means you are uncertain about the true data generating process, and then you are necessarily also uncertain about the aleatoric uncertainty because this is a property of the data generation process. Yeah, and therefore you can really be sure about aleatoric uncertainty only or epistemic uncertainty is gone. And this means that this additive decomposition is really a little bit doubtful, right? In principle, as long as your epistemic uncertainty is greater 0, you can't expect that you can precisely quantify your aleatoric uncertainty. And this figure here shows this quite well. I mean, what you expect, of course, is that your total uncertainty decreases with increasing sample size and converges to the aleatoric when all epistemic is gone. So you get these curves. But if you take the aleatoric as the difference between the two, you get this dotted line. But actually, our aleatoric uncertainty, because it is a property of the data generating process, doesn't change. So it's actually constant. Okay. So we have been working recently. Sebastian checks the time. Yeah, it's my last slide. We have been working on alternative ways of quantifying uncertainty. We're not going to detail here because, yeah, keep an eye on the time. One approach is distance-based, not based on information theory, but distance-based, where we use Wasserstein distance to basically measure how much effort do we have to invest to turn a second-order distribution into a first-order or zero-order distribution to get rid of the uncertainty. Another one is loss-based, so to say, and takes advantage of this notion of a proper storing rule that I already mentioned, which is known to be decomposable into what is called a divergence term and an entropy term, and these again qualify in a sense as meaningful measures of aleatoric and epistemic uncertainty. Okay. But now, let me quickly conclude. I think we all agree that designing reliable and uncertainty-aware learners is a very important topic, given all these real-world applications of AI we have today. Distinguishing between this aleatoric and epistemic part is also an important thing to do. I would argue from a knowledge representational point of view, makes perfect sense. However, especially this epistemic part is really hard to tackle. In particular, what I have shown today is this negative result showing that a specific approach on which currently quite a number of papers are written. I mean, this is why I think this is not unimportant. Cannot work, at least not theoretically, which is not very constructive, but still interesting, I think. Yeah, so the big question still is, to what extent is it anyway possible to train machine learning, predictive machine learning methods which represent this second order uncertainty, this epistemic uncertainty in a more or less objective manner. And yes, as usual, there are many open problems. Anyway, you have seen it's still far from settled, the whole field, many open questions. So, for example, what do you do with model uncertainty? Is it maybe a good idea to go for other uncertainty formalisms? I mentioned these Weaver sets already, this Janssen-Shaper theory, and so on. Can they do better than standard probability theory, etc.? And of course, also there are many interesting applications in topics like active learning. We've been speaking about Bayesian optimization before, and so on and so on. Okay, here's a couple of references. I thank you very much for your attention.
Thank you very much, Eyke, for this very interesting and also thought-provoking talk. This was great. We have some time for questions and comments.
Yes, thank you for the nice presentation. I have two questions. The first